Hi there, my name is Heidi Howard. I'm a research fellow in computer science based at the University of Cambridge. So this week I read an interesting paper on the topic of data synchronization in distributed systems, and I thought I would spend the next couple of minutes sharing the paper and its results with you. So this is the paper. It's called Low Complexity Set Reconciliation Using Bloom Filters, and it was published in 2011 at a workshop on the foundations of mobile computing. So this paper is on the topic of set reconciliation. So this is the problem of how to compute the union between two sets over a network. At the high level, this paper proposes using Bloom filters for this set reconciliation. And the way that they do this is by sending small Bloom filters back and forth to enable the two sets to converge towards the union of the two sets. So let's take a look at the problem that this paper is trying to solve. So imagine that we have two nodes. We've got node A and node B. Node A has the set of elements 1, 2, 4, and 5, and node B has the set of elements 1, 2, and 3. Once the algorithm is complete, we would like both node A and node B to have the set 1 to 5. So one way we could do this is we could have node A send their entire set to node B. Node B can then compute the union of its set and the set it received from A. It can then respond to A with the elements that A is missing, in this case just 3. Node A can union this set with its own set to get the complete set. The problem with this approach is that you're having to send these entire sets over the network. And this can be problematic when we assume that these sets are usually quite large, both in terms of the number of elements and the elements themselves are large. And this is unnecessary because if you look, both node A and node B in this example already have elements 1 and 2. So we don't need to be sending elements 1 and 2 back and forth. This is the problem that's solved in this paper. This paper proposes using Bloom filters to solve this problem. Bloom filters are a data structure for recording set membership. What we can do is we can have node A create a Bloom filter with the elements 1, 2, 4, and 5. They can then send this Bloom filter to node B. Node B can look up its elements 1, 2, and 3 in the Bloom filter. And when it looks up 3, it will discover that 3 is missing, and therefore it will send 3 to node A. It will also send a Bloom filter of its elements, which node A can use to determine that node B is missing elements 1 and 5. Bloom filters are space and time efficient, and so they're a good data structure for this application. However, there's a substantial downside of them that is being completely ignored in this example, and that is that they can give false positives. So a Bloom filter can overestimate set membership. This algorithm approaches this by running multiple rounds. So imagine that instead of sending both 4 and 5 back, actually, node A only sent 4 back. This is because when node A looked in the Bloom filter for element 5, the Bloom filter gave it a false positive. It said, oh, B already has 5, so you don't need to send it. However, the algorithm's going to run another round with the Bloom filters again, and this time node A will realize that element 5 is missing and will send element 5 to node B. And this is how the algorithm works. So it goes through many rounds, and as it does so, the sets grow and they converge towards the union of the two original sets. What's really neat about this algorithm is that they're able to compute exact set reconciliation using an approximate data structure. I didn't show it in the example, but these nodes are also exchanging hashes of the sets that they have, and they're using this at each stage to check whether their sets are the same, and when they detect that the sets are the same, the algorithm terminates. Assuming a collision-free hash function, the algorithm will always converge such that the final sets on both nodes are the unions of the original two sets. The authors of the paper implemented and evaluated the algorithm. They compared the number of rounds and the communication overhead for varying different set difference sizes, from sets that are different by just 10 elements to sets that are different by 10,000 elements. And we can see in the evaluation that the number of rounds and the communication overhead scales quite nicely as the set difference increases. Overall, I really enjoyed reading this paper. I would definitely recommend this paper to anyone who's interested in the problem of data synchronization and set reconciliation in distributed systems. I think the paper is very approachable. It doesn't assume any background knowledge of the area. For example, it describes Bloom filters from the ground up, and it does a nice job of evaluating the algorithm and explaining honestly the limitations of the algorithm. For example, its non-optimal use of bandwidth. That's all I have to say for now. I'm going to put a link in the description box to this paper and a couple of other papers in this area that you might be interested in. If you have any questions about this paper, please leave them for me in the comment section down below. Thank you for listening.